Besides shell sort, another popular variant of regular insertion sort is an algorithm called binary insertion sort. This algorithm, unlike shell sort, does not improve on regular insertion sort by avoiding costly turtles. No, the algorithm does not make use of any gaps. It actually traverses the unsorted section of the array one step at a time. Binary insertion sort, however, focuses on the sorted section of the array. It is here where binary insertion sort does things a little different. Instead of going through this section of the array one step at a time, it makes use of the fact that this section is sorted. It kind of works like as if you were going through an old-fashioned non-digital phone book. If you're looking for a surname that starts, say, with the letter T, you would not start at the first page of the phone book and then work yourself through hundreds of pages one step at a time, one page at a time, until you finally reach the first page with surnames that start with the letter T. No, you will probably open the phone book somewhere in the middle, maybe even with the slight bias towards the end of the alphabet, and then check whether the name on that page that you just opened up comes before or after T. And if it comes before T, you know that you don't have to search the first half of the phone book because none of the names on these hundreds of pages will start with the letter T. You know that the name that you're looking for must be somewhere in the second half. And now you will repeat the strategy for the second half and so on until you found the desired family name. And just like that, you will have run binary search. And this is what binary insertion sort does too. Now, if this wasn't 100% clear yet, let's head over to the numerical example. So I am now in a new script that I call binary insertion.py. And here we'll now start by going through this example with our unsorted array being 2, 5, 4, 1, and 3. Now, in the first traversal, we'll not going to start with, we won't start with the first element, but we'll start with the second element. Well, why is that? Because just like as with regular insertion sort, there is no need to look at this section of the array because if it only includes one element, by definition, this section of the array that now only includes this two is already sorted. So we're looking only at this element. And this is now called the key element. So 5 is our key element here. And now we are looking at this unsorted section of the array. And as I just explained, this only includes this 2 at the moment. So I'm using these little circles to indicate the sorted section of the array. And we now realize that this 5 is greater than whatever is in this sorted section of the array. And the sorted section of the array, we only have to look at the last element to make the statement that 5 is greater than anything in that sorted section, okay? Later on, we'll see that the sorted section will include more than just one element, obviously. And then it's always this last element that we are comparing to in terms of determining whether or not it's greater, whether or not the key element is greater. So here we see that 5 is greater than the last element, and thus every element in the sorted section. So we don't have to do anything here, and the array just continues to read 2, 5, 4, 1, 3. Now comes the second traversal. Here, we are now looking at 4. Now, 4 is the new key element, okay? So we are now looking at this 4, and we are comparing it with the sorted section of the array. And now the sorted section of the array, which, again, I'm using circles to indicate, now includes the 2 and the 5. And here we are now seeing, okay, this 4, it has to go in between 2 and 5, because it's greater than 2 and less than 5. So 4, the key element, is going to be inserted between 2 and 5. Now you might be asking, well, how do you know that it has to go between 2 and 5? And this is actually the critical part here, and I'm going to explain that in a minute. Let's have a look at the third traversal, though, first. The third traversal, I'm now looking at this 1. This is the next key element. I'm comparing it again with the sorted section of the array, which now includes 2, 4, and 5. I now see that 1 is smaller than the smallest element in the sorted section, so it has to go to the very front, and the array now reads 1, 2, 4, 5, and 3. Now comes the fourth, and as it happens to be at the final traversal in our numerical example here, we're now looking at this 3, which is the last key element. We are comparing it against all the other elements in the array, and we have to insert it between 2 and 4. Okay? So this is now how binary insertion sort works, but for that matter, this is also how regular insertion sort works, because I haven't really told you anything new here. The only thing that I did differently as compared to regular insertion sort and the numerical example that I showed you there is I kind of highlighted this sorted section of the array a little bit more by using these circles. So the question now is, well, within this sorted section of the array, how does the computer know where to insert the key element? And this is the key question, haha. So the question is, how can we determine the correct position of the key element within the sorted section of the array? Now, to make this point a little bit easier to understand, I think it's a good thing to actually look at an array that's a little larger. So we might have an array that looks like this, where this is only the sorted section of the array. And the sorted section reads 0, 1, 2, and now comes 4, 5, 6, 7, and so on until we reach 15. Now comes a key element, which is 3. And after this, we might have a bunch of more elements coming all the way over here, but we're now really only looking at this 3, which is our key element here. And the question now is, where are we going to insert this array element in the sorted section? And this is now where this phone book analogy comes into play. Now, imagine 3 being a last name. Say the last name was starting with C, for that matter. Third character for third letter in the alphabet, right? So let's pretend this was C. Now, in the real world example of a phone book, I mean, people aren't really using non-digital phone books anymore, but let's pretend we are. We would take this book and we wouldn't really search the second half of the alphabet because, I mean, it's C. It's probably going to be in the beginning unless we live in a city where almost everybody's last name started with A or B, right? But since this will most likely not be the case, we don't really have to focus on most of the letters in the alphabet and therefore most of the sections in the phone book. And binary insertion sort now does something that's not too different. Binary insertion sort looks at this entire unsorted section and says, well, what's the middle element of this? Well, we have 7 elements to the right, to the left of A, and 7 elements to the right of it. So 8, in this case here, is the middle element, the center element of this sorted section of the array. Remember, the array includes this 3 and whatever comes over here. This is only the sorted section, and 8 within this sorted section is the middle element. And now the computer says, well, I'm just going to compare 8 and 3. And I realized that 3 is smaller, so it has to come in this section over here. Somewhere in here, this is where 3 will have to go. It's not going to be in here. Just like we know that there's no point in searching for last names starting with C in a list of names which all start with, say, D and greater. There's no point in doing that. We know it has to be somewhere over here. And now the computer says, well, let's just repeat this step that I just did once more for the remaining section of these. Well, the remaining section of the sorted part of the array. So now the computer in the next step is only going to look at the numbers from 0 to 7. And here, 4 is now the new middle element. 3 elements to the left, 3 elements to the right. Again, we can observe that 3 is smaller than this middle element. So we are now only going to have to look at this section of the array, 0, 1, and 2. Here, 1 is the middle element. 3 is greater, so we know that it has to come in this section of the array, which now only includes 2. So we are now looking at this last step here where the part of the array that we are now looking at only consists of one single element, 2. Okay? And we see that 3 is greater than 2, so we have established that 3 will come immediately or just right after 2. And this will now be the correct position. And the cool thing about this procedure is that it took us a lot fewer steps to get there instead of comparing every element from 15 and down onwards, okay? Down to 2. So had we used regular insertion sort, we would have taken that 3 and we would have said, well, 15 is greater than 3, so let's copy this over. Then compare 3 to 14. 14 is greater. Let's copy this over. compare 3 with 13. And this would have gone on and taken forever until we would have reached this point down here where we would have said, well, 2 is not greater than 3, so this must be the correct position. And this would have been a lot more steps than doing this procedure here, where just within the first step, we are already ruling out half of all the numbers here. Now you might say, well, 3 was kind of lucky for you here because 3 is at the very beginning, but this pattern here just extends to most instances that you run into. Okay, so most of the time, binary insertion sort will offer a tremendous increase in speed. Now, of course, say that this was 14, and okay, so there wasn't 14 here, and we had 14 over here. In that instance, regular insertion sort would have been a little faster because it would not have involved going through all of this, then only this, and then only this bit, and then finally making the right call. Now, here, regular insertion sort would have been a little faster, but in most cases, binary insertion sort is a lot faster, and on average, trust me, it will make a big difference. So let's get ready to code this. So I'm going to go down here, and I'm going to define a new function. I'm going to call this, well, binary insertion sort. And we'll have one parameter, which is the array itself. We'll define in our local variable. And now we'll have a little loop to traverse the array. And we'll now say for I in range. And now where am I going to start this? Well, as you saw with the example, just like with regular insertion sort, there's no point in looking at this element because by definition, it is already sorted. So we really only have to start our search for, not search, but our, well, loop through all the key elements at the second array element. And the second array element in Python, well, that's 1, right? It's indexed 1. So we're going to have our loop go from I until n. Now, well, what are we going to do? Well, we're going to store the key element, store the key element. So we'll now create a variable called key, and this will be the array element at index position I. Now we'll have to find the correct position for the key element. And here we're not going to code this right now, but we'll just say, we'll call a function called binary underscore search, and this function will return the correct position j of where this key needs to go. So now here we are now going to insert the key element, and well, how are we going to insert this? Well, say we now know where it needs to go. So if we go back up here, we now have this sorted section of the array, then comes the key element, and then come all the other elements. And we now determine that it has to go between here, between this 2 and this 4. So in our loop, this will be I. So the position of where this 3 is right now, this is I. And j will be this position here. So everything from the first element up until j, not included, this will be just like as it was before. So here we can now type that a, and here we can say from 0 to n. So that's really just to make clear that we are now building this array step by step. At first, we'll have everything up until j, and j is not included. So we can just use this notation here where we have the colon and nothing before it, saying before j, just use everything as is, and then up until j, but j not included, okay? After that, well, we are now going to insert the key. So now we'll type the key, and we'll put this in brackets so that we can paste these and combine these different sections or parts of the list together. Now, what comes after the key element? So we have now put together this array including 0, 1, 2, now this 3, and now comes everything after j all the way up until I, but I not included. Remember, this was position I, so we now have everything from j going all the way over here until I. So this will be the next section that we have to add here. So now we have j up until I. So j, remember, because of the way that Python does its indexing, the first element here is always included, but this second element here that's mentioned here after the colon, this will not be included. Just like j was not included here, I will not be included here, but j now is. So we now have everything j included all the way up until I, which is not included. And after that, so now that we have everything up until this point, and this 3 is already put in here, we now have to just paste everything that comes after it in the unsorted section of the array. We now have to add this to here, and then everything will be in place. So here we now have everything from I plus 1. We don't use I because I, well, that's the key that's already here. So I plus 1 until, well, however long the array is. So I think we could put n here, but I don't think we have to, okay? So this is where we are going to insert this and how everything's going to come together. Now for this to actually work, well, we have to define the binary search function. Otherwise, well, this function here, binary insertion sort, cannot call it. So let's define this function, binary search. So this function is going to take a bunch of parameters. First, it's got to have the array and it's got to have the key element. And then, well, the way that this is going to work, it's going to be working by recursion, right? So it has to do this pattern here of first looking at the entire sorted part of the array, and then only at 1/2, and then only at 1/2 of that, and then only at 1/2 of that. So it has to be able to do this recursively. For this part here, then it has to look at the first half of the first half, which is what it does here. Now it's looking at the second half of the first half of the first half. It's getting kind of difficult to say all of that, but it has to like keep track of where it is because it's not always from 0 until, you know, half and then the half of that and then the half of that. No, it's kind of like going back and forth. If it's really searching every part of this binary tree, this is really what's happening here. And therefore we have to keep track of where it's starting, where it's ending, and where the position of the key element, of the original element was, okay? And now we'll have to determine the mid element. So we can do this, the center element. I'm just going to call it middle, I think. Well, that will be round. I think we can use the round command here. We can just add start and end position and divide that by 2. So let's go back up here. This is, let's say, well, this is start and end, so this would go 0 until over here. We add these 2 index positions, divide by 2, and then we'll get this number, okay? And, well, remember not 8, but the index position of where that is located. And this is how we determine the middle element. So now that we know that, or where this middle is, we will have to make the following comparison. So if the middle element, so now we are indexing A at position middle, is less than the key, or if the key is greater than that, well, we are only going to be searching everything that comes to the right of the center. So had this not been 3, but had this been 9, we would have said, well, 9 is greater than 8. So we can dismiss all of these numbers from 0 up until 7. We only have to look into this part here. So everything before the middle element can be ignored. So now we are repeating our search. So I'm going to type return binary search once more. But here we are now not going to go through this entire array once more. But we are not going to be starting at start, but we'll start at middle plus 1. Okay, and this is what's happening here. So we are not searching everything once more, but only the second half. Now, the second thing that can happen is, well, it can happen that A of the middle element, that this is greater than the key element. So here we'll now also run a binary search, but we are not going to start at the middle plus 1 element, but we are going to be starting at the start because now we are searching the first half. Except that end will now not be end, but middle minus 1. And then lastly, we also have our position in here. And here I misspelled return. Okay, so you can kind of see how this works, how we are now searching the right-hand side, and here we are searching the left-hand side. And in case we are exactly on this middle element, well, here we'll just return middle, okay? And yeah, there's unfortunately one more thing that we have to do. The computer now only knows what to do if there's an actual array to be sorted. So it's kind of like only covering these steps from here all the way down here. But what happens if start and end are like equal? If you're looking at this last thing here where there is no possible way of splitting this up any further. So this is what we'll have to take care of. So here we'll now type if start is equal to end. Well, if that's the case, if a start, so if the starting element, is greater than the key, well, we can just return start, right? So start is greater than the key is less than that, so it has to come before that, so here we'll now return the start. And if else, well, in that case, we'll return start plus 1, okay? So it's the end, and I mean, you could also say end, that's the same thing. We could say end plus 1, maybe that makes it a little bit easier to understand, but it doesn't really matter because start and end are equal, okay? And then the other thing that could happen here is, well, we'll have this elif of start being greater than end. This is only in terms of like when we are searching and we're very far down and weird things happen here. So in that case, we'll just return the start, okay? And then lastly, we'll have this else statement of else, which is kind of like the regular case of we are going to go determine the center, the middle element, and then from there we'll go to the next level of recursion. And yeah, if I'm not mistaken here, that should be it. That should be how we can run binary search. So let's define an array. And I'm just going to use this from up here. And I think in the binary insertion sort function, once we're done with all the sorting, let's just print A. And let's run this. So binary insertion sort A. And up we get an error because, well, okay, we haven't used all of our new elements in this binary search function here. So A and key, well, that's just the same notation that we've used here. But what's the start? Well, we're going to start at the very left. And we are searching until I minus 1, because I is already the key element. We're only searching the sorted section of the array, and the key element, well, that's positioned at I. I'm going to run this, and now we get this 1, 2, 3, 4, 5. So the array is now sorted. So let's remove this. There's now only one thing left to do. Well, we have to visualize this. So we have to yield from our binary insertion sort function. And I think the best way to visualize this is to yield before we insert the key element. So here we can yield the array, and now we will highlight I minus 1, which is the element that comes right before the one that we are now inserting. And then we are highlighting the position of where it is that we are inserting this, okay? So we are highlighting the end of the sorted section. The one after that is the one that we're now trying to find the right spot of, and then J will be where it has to go, okay? So let's try and see whether this works. So I'm now in my animate script. I'm not going to import this. So from binary insertion, we are going to import, oh, this is false, binary insertion sort. We're going to add this down here. So I'm just going to copy paste this and type binary in front of it. And here we'll now have binary underscore insertion sort. Don't use this comma here. We're going to go into the main and we're type binary insertion sort and run this, and voila, here it is. We can now see how super fast this algorithm works. Let's reduce the speed to something a bit slower, 50 maybe, and we can see that, well, it's now always highlighting this end of the sorted section, and then it's just showing us where this element is being inserted. If you wanted to, we could also highlight everything in this sorted section. So we could have, say, make this a list of a range, list range 0 to I minus 1. Let's see what that looks like. So now, okay, actually the range command, well, here we all type I because remember, this is not included in the way that Python indexes, so it's only going to go until I minus 1, which is exactly what we want. And now we can see, yeah, the section of the array that is already sorted, and now it's just popping up where the next element is going. And yeah, this is just going so fast. It's so hard to track this, so I'm going to start this once more with, say, only 50 elements. and a speed of, I'm going to make this 2. So this will be very slow. So yeah, we can now see that the next element will be this one right here. And it's going to go pretty much where this yellow bar is, because it's going to go between this bar here and this bar there. So I'm not going to try to unpause this and then quickly repause it. Okay, I was too slow. It's just so fast. Oh, remember, no. J, if I go back over here, yeah, this is already the correct position, but I'm afraid that I can't pause and so quickly unpause it for us to see what's going on, right? So this is going so quickly. And yeah, but I think this is it. I think this is working the way it's supposed to. We can now increase the speed here, make this run faster. Okay, this is going to take forever to increase the speed like this, but yeah. The animation is working. This is what we wanted. I hope you enjoyed this video. Yeah, this is binary insertion sort. It's actually not that hard to code. The only thing that's kind of difficult is to get your head around is this binary search function, but we'll come across this in just a couple of videos down the road once more. Well, not just once, but multiple times when we look at things like heap sort and merge sort. So recursion will pop up every now and then in our series. But until then, let's just enjoy our beautiful animation binary insertion sort running at lightning speed through this array. Thank you very much for watching. I hope to see you in the next video. Bye.